Hello, my name is Logan Hazer, and this is my video for my honors contract. What I created was a intruder detector. The way this works is you see that yellow light on the Arduino and the blue light here from the Atmega. The way this works is that the Arduino is reading the value from this light dependent resistor here, which is kind of hard to see. That's a light dependent resistor right there. And once it reaches below a certain threshold, it turns on its light and sends a Y over to the Atmega. The Y means yes, there's an intruder. And the Atmega turns on its light as well. So since there's no light hitting the laser's not hitting the light dependent resistor right now, there's an intruder because it's breaking the beam. So let me show you what happens if there's a beam on it. So I have this handy dandy laser here. So if the laser, it's kind of hard to hold this still while having the laser face it. Okay, so see that right there? That's the laser hitting the light dependent resistor. When it's right on it, both lights go off. When something gets in between it, they both go back on. When it's on it, they both go off. On. Hold on, sorry, it's hard to position this while watching the video. There we go. Off, on, off, on, off, on. So whenever an intruder walks in between the lights, it triggers a method that sends the data, a Y for yes or an N for no. So the way that works is if the beam gets interrupted, the Arduino sends a Y to the Atmega. If the beam is not interrupted, it sends an N, which means no, there's no intruder. I could modify it so that the light stays on for a longer period of time, but the idea behind it is just to show that you can acknowledge that something happened and then have that data to trigger some sort of event, like calling the police or, for example, maybe sending a tweet or texting someone, something like that. So yeah, that's what it does. Let me show you the code, and yeah. Alrighty. So if we go over here to my Windows machine, and we open up the sketch here, as you can see here, we're using the analog pin A0 to read in the input from the LDR, and we have this thing to read that holds the value read. First of all, we begin the I2C connection with the wire library from the Arduino. We begin that, and we set the built-in LED, which is that tiny yellow one. It's this tiny yellow one there. That's the built-in LED. We set that one to output. Then if we scroll down, here's our loop. It reads in the analog value from the LDR pin. If the value is less than 500, then it writes the LED high. And because we use the voltage divider over here, I don't know if you can see that, but there's an LED there. Not an LED, I mean there's a resistor there, and there's the LDR. The blue resistor there causes the value to be really low when there's no light. Because normally, if you don't have the voltage divider, the LDR will have a wider range of values it goes through. But with that, it pulls it high or low, like, pretty easily. But anyway, so that does that. And then, so yeah, so it calls alert intruder if the beam has been interrupted. Otherwise, it calls no intruder, and then it delays it for 200 milliseconds. So if you scroll down here, here's alert intruder, it sends Y, and no intruder sends N. And if you look up here, we have this method I created called sendByte. What it does is it begins transmission, and this is the address of the Atmega, which I configured. So the address for the Atmega is 8. The way that the wire library works, you do not need to set the 1 or 0 for whether or not you're reading or writing. You simply send the address, and then you call a different method depending on what you're trying to do. Here I'm just sending the data, and then I end the transmission. So that's on the Arduino side. Let me show you the Atmega side. So if we come over here, and let's see, yeah, here we go. Alright, let me scroll up to the top. Alrighty, so the LED is on PB1, which is why I have this here, although I don't think I use this, so I should actually probably just delete that. So first thing we do is we init useart. This was used for debugging and also is used for, it can be used to see what values the Atmega is actually getting, which are Y and N. And then I created my custom I2C setup function. So if you scroll down here in the I2C setup function, we have to set the address register for the Atmega, for the TWI. This sets up the slave address as this comment says here. And this first bit here is just to enable the general call, which enables the Atmega to respond to the generic address 0x00. However, the other 7 bits after the first bit, these are the actual address for the Atmega that it will respond to. So right now it's responding to 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, or 8, which, as you noticed a few minutes ago, we were writing to the value of 8 with the Arduino, which is why it's working. This is copied from, this line's copied from the I2C was it I2C.h? Yeah, the one from the book. They have their own function for setting up the I2C communications. This sets the bit rate. And as you can see, the author's comment has a page reference as well. And then here we set up the TWI control register. The reason why I made my own custom one is because I needed to enable the acknowledge bit, which allows the Atmega to respond to its slave address, which we set up here. And then I have this delay here just because when I was experimenting with it, it needed a delay, otherwise the communication wouldn't work. So that's that, and then after that, we set up the DDRB to enable PB1 for output, which is for the LED, indicating that we have an intruder. And then I have a variable to hold the data that we get from the Arduino. So this is really simple. I indented it just to make it easier to read. These are actually all basically in the same line, but whatever. So the way it works is it loops until the TWI interrupt bit in the TWI control register is set. This bit will be set whenever the Atmega gets addressed, whenever whenever the Arduino sends data that has the address of the Atmega. So once this gets set, we know that we've been addressed. So what we do is we get data from the I2C, but we do an I2C read acknowledge. Because if you call I2C read noack, it'll disable the enable acknowledgement bit, which will make it so that the Arduino, it will make it so the Atmega can no longer respond to its address. It will no longer receive data because it is no longer listening for data. You can actually manually turn this on and off, this bit here, to remove it from at the I2C communication circuit in a way. If you turn this off, it will no longer respond, and you can turn it back on when you want to respond again. So you get the data. If the data is a Y, then it turns on the LED. If the data is an N, then it turns the LED off. So as you notice, there's no delay on this side because the delay is on the Arduino side. The Arduino waits 200 milliseconds before it updates again. This one does not have to wait because it only reads data when the Arduino sends it. And this also makes it so that they're in sync. If they both had their own delays, then there could be issues with the way that the timing lines up. But yeah, so that's how this program works. Yeah, it's pretty cool. I hope to extend it in the future with a Wi-Fi module I bought and connect it to a server and make it so that it can send push notifications and things like that.